Alice will stay through the next session.
All right, now we'll pass on the solutions to everyday digital problems. And we'll start with Nicolas Pouillon, which is a system developer for Ellisys. Ellisys is a supplier of advanced protocol test solutions, are based in Geneva. And Nicolas is going to talk to us about software abstraction techniques for interface modeling using VHDL. So, yes.
Hi, thanks for the introduction. So I did a PhD some time ago in computer science and electronics. So basically, I was implementing abstract platforms like SoC virtual prototypes. Yeah. And then I went to a software company, basically doing consumer market electronics. And at some point, I wanted to play with I wanted to play with VHDL. At the time, it was not my job yet. And so roughly 10 years ago, I started a library because I kind of looked around what was available and was not satisfied what was available. So I wrote my own. And I engineered it at the time as a software project, which means I have built system code level dependency management, strong typing. And roughly, it's not as it's usually done is in hardware. And at some point, I needed to interface with standards, industry standards. So what was the question again? Have you encountered some common problem and solved it in a way you want to share? So yes, there is. Of course. No? That's terrible. Let's revert back to PDF. Sorry about this. Damn it. Sorry. What did you say? How do you go full screen? Sorry. Yeah. So my problem was to build a set of IXI-based models in a way we can reuse them in the long term, and to be user-centric, because as it's engineered as a software project, I somehow try to build a library in terms of reusable code snippets. And of course, have compatibility with all the current tools, because I want to go to hardware today, not with some crazy language feature we'll have in 10 years in tools. So let's start with IXI Stream. IXI Stream is the basic data moving interface. And actually, if you take the specification, it has a lot of optional features. And actually, everything is optional except one signal. Can you guess which one? Well, actually, the only required one is valid. Even data is optional. It can be 0 bytes wide. So in the end, there is way too much flexibility in the specification. And if you want to do a stack of reusable models, you end up having crazy code with way too many options. So my first idea was, how do we make this manageable? Of course, the first thing is to group signals, because we will basically avoid having extra long port mappings. But if you start to use records with currently available constructs, you have a problem of dimensioning the IOs to match every case. So basically, you end up having ports that are overly big, that can hold any type of configuration. And then you add a configuration record as well to just say what subset of this overly big signal I will actually use in my model. And to make this manageable and not having to do extraction by hand every time, you just put functions everywhere to either write to signal ports or read from them. This may seem scary like this, but actually most of the time you only pass very few parameters, arguments to functions, and the rest of it is like taking the default values. Then we can start to add some more sugar around the library, because as we manage all the signals to functions, we can actually tailor functions to use the data with backend specific, with model-specific usage of the actual stream interface. So let's say a stream interface, if we stick to the standard, it's a bunch of bytes that comes through a FIFO. And we can actually see this stream of bytes as a stream of integers of variable width. But if we have integers, are they big endian, little endian? There are many different ways to model this. And the idea here is to say, OK, I will dereference the signals through a function that will extract what is actually configured as the working subset and extract it with this given endianness. So here it's the same stream, and I can read and write from it either as a bunch of bytes or as as one integer. By default, it's little endian because AXI is little endian by default. But you may say, OK, actually, I want big endian, and it does the conversion for you and returns you an unsigned value. Then we may think, OK, we made overly big signal records, and in the worst case, in the worst case scenario I actually implemented, for a full AXI stream interface, the worst case is more than 700 wires, which is not manageable. But what are the options to do optimization about this? So of course, we'll rely on the tools to actually strip unneeded signals. But how to convince the tools that the signals are actually useless? The first thing we can do is to take the configuration and say, OK, configuration says, for example, there is no back pressure, like ready should not exist, and you can always send data. There is no back pressure. So just return constant true is ready is always true. The same goes with keep. Take keep in AXI stream is a way to do sparse streams, like to have streams where you have, let's say, 4 bytes width, but sometimes you send in one cycle only 3 significant bytes. By default, if you do not enable this feature, all the bytes are significant, so it's all ones by default. But then there are even more tedious things. In AXI stream, there are 2 byte masking features, keep and strobe. Strobe say the byte is not significant in the stream, but please leave room for it. And keep says this byte doesn't exist at all in the stream. And by default, the specification says if, that's the second line here, it says if strobe is absent but keep is present, store defaults to keep. That means with just port mappings, when we do a generic model, we cannot implement this properly without having conditionals in the actual code that reads from the signals, because the default value of one port cannot be the other one. But here we can do this because the function that is supposed to dereference strobe information out of the signal has access to all the subsignals. So it can fall back to keep by default. Of course, to make it extra obvious to the tools when we write to signals, we actually, behind the hood, put don't cares everywhere in a way the tools will basically just strip the signals. And we try not to read from the signals. And sometimes states machine will dereference constants, and of course the tools will try hard to remove all the matching states that are unreachable. And then we can start to add some syntactic and library sugar. The first thing, of course, is to have dumpers that are able to pretty print IXI stream. In a way, it's extra obvious to the reader what we actually convey. And here we have the last line of the log is actually saying, OK, I have a 12-byte stream. Only 8 bytes are significant, and the 4 last are with keep disabled, so they are absent from the stream. We can also convert from and to learn signals. This is basically the path to interoperability with the rest of the world. Either Verilog, Xilinx, block design, whatever needs to have all the ports detached. And this is modeled as one block that does the thing, whatever the configuration, as long as it makes sense, and just works. Validated once and works. We can, of course, have protocol assertions. And another, it's like a corollary of the from tool and signals. It's a way to package the structured type to a bunch of wires, like a vector of wires. This is the basic block to build everything that is related to storing a stream. Like when you have a FIFO or a clock domain crossing or any other encapsulation of a stream over something else, the first thing you need to do is to take the whole bunch of signals and make them a vector. So this as well can be done with functions that actually return the relevant bit widths, exact bit widths, and you can pipe this to all your usual already validated basic elements that do clock domain crossing and FIFOs and everything else. For the usage, the general usage, when we have this kind of abstraction, the port mapping gets concise enough that it's manageable. And this makes it handy to use. In a way, we don't have to rely anymore on netlist generating stuff like block designs, because authoring this kind of code gets manageable. Now, if we focus on the width adapter here, it's basically converting a stream from a given aspect ratio to another. So let's say the input is 4-byte wide, the output is 12-byte wide, and here in the drawing we have 20 bytes of data that comes in 5 cycles, and it gets output to 2 cycles, one of 12, one of 8, and 4 extra empty bytes with keep false. When we try to actually test this, of course, our test benches want to focus on semantics and not actual encoding. So here, the whole idea is to have functions that are, well, it's actually methods that are able to send and receive from signals whatever the shape of the stream. because then we can change late the actual shape of the stream, and nothing changes anywhere else in the code. Because we focus on what is actually the block doing and not how it's doing it. And of course, the dampers adapt as well. Like, there is no change at all. We just give them the configuration, and they just dump whatever the width is supposed to be. We can start to add more utility things. One of them is a read-write buffer. One thing we actually have at Ellisys is full HDL USB device implementation. USB 2 and or USB 3. And when you actually implement USB 3, you have to go 5-10 gigabit per second. So you need relatively big data path, like usually 32 bits data path. And when we do this, of course, it has a cost in terms of footprint. On the other hand, when we are doing USB 2 only, we can afford to have only 8-bit wide data path. So at some point, we may have a trade-off between throughput and resources. And like here, for the example, we have a block that is processing a stream and inserts a header before the stream. And maybe we want to design a block that is able to adapt to be either 1, 2, or 4 byte width, and to do it late in the implementation. And how to design this? Well, again, as long as we have abstracted everything out, we can add a configuration for buffer, and just here, when we see a packet that presents itself when we are idle, we can actually snapshot the header and then put the header and stay in this header state as long as necessary to actually output the whole header. And actually, the isLast here will tell whether it's the life cycle we should actually be there before getting back to other processing. And this will magically, not so magically, but automatically be staying in this exact state the number of cycles necessary to output the header. So in the first case, the header is split in 4 bytes, and it will be outputted in 4 cycles. In the second case, we have 2 times 2 here, and they will be output 2 by 2. And in the last case, we stay in the state only 1 cycle. And the nice thing is, the isLast here, when we are in the third case, is always true, because we only need to stay in this state only once. So everything disappears, like the test disappears, and the state machine basically just goes to the write state directly. We can do this with both read and write. If we move to AXI memory mapped, it's like AXI stream with the same kind of flexibility, but we have 5 channels instead of 1. And everything is optional, roughly. We can apply the same concepts. You get the idea. And we can have the same kind of niceness in terms of blocks. And in the end, there is something that somehow happens in AXI stream, is to have bursts. Burst is the way to convey more than one chunk of data with one command. And bursting implementation is actually super flexible. And to grasp correctly, if you have the knowledge to work with this kind of design and you come every 3 months on a design like this, you kind of forget all the time what are the rules, actually. And they are in the specification. Like, there is the pseudocode for how to handle a burst. And of course, this is the kind of boilerplate code you have to re-implement in every slave that implements a burst, which of course is supported used to validate and debug. So let's do it once, like move the initialization part and the loop part to 2 functions. and transparently make it handle everything. And here on the right, I don't know why it's shaded. Here on the right, it's the full right side of a bursting memory block. Like it's implementing the full memory interface to an actual memory block. And we take the address at each iteration from the transaction block, and to generate the response back, we have to echo back ID and user, and we take them from the transaction context. Is this totally universal? Well, maybe not, but it applies to a big bunch of things, including data processing. And one of them is all the class of problems around CSE. You probably somehow, at some point, have the need for a CSE block. Let's say we have a CSE block that takes 32 bits at a time, outputs 32 bits at a time, and processes it. So you go to a generator, create a big bunch of XORs like this, and it's more or less unmaintainable. But we could write it like this as well. Like have a static constant that is the parameters where we show the polynomial, the initialization value, how we process the bit stream, how we output the values. And actually, those two architectures are strictly equivalent. They provide the same results. They synthesize to the same exact logic. That's basically the same output. But one is manageable, the other is not. And the key point is, oh, yeah, we changed the architecture. We don't process 32 bits at a time, but just 8 bits at a time. Well, you go back to the generator, generate another wall of XOR. But in the other case, you don't change anything because it's all magic. Of course, same concept. Have a factory to handle the parameters, store them in a constant, have a bunch of functions that do the processing. And the nice thing here is we can also use it from test bench in linear code, not from FSM code, but actually the snippet on the bottom right is creating for test benches an Ethernet frame with the FCS appended from Bucket. Of course, we can do crossovers between libraries and have, let's say, a block that does appending CSC to any shape and any type of IXI stream frame, and you just supply two configuration constants to the block, well, generics to the block. The one is the stream configuration, the other is the CSC configuration. And the actual implementation takes less than 120 lines and is totally agnostic to whatever the shape of everything. So the takeaways. By designing this way, we can isolate the net listing problem from the actual implementation, and we can remove a lot of boilerplate code. That is what is actually the incentive to go like HLS is to say, oh yeah, but you can do late design trade-offs. With this, we can actually have some of the benefits of HLS in pure VHDL. And it's pure VHDL 93, so it has the maximum compatibility with any tools out there. Thanks. Yeah, I forgot to say it's available on GitHub. You have the URL there.
Thank you very much, Nicolas. We are about to ask you actually where can we find all that. Any questions, please?
Yes, many thanks for your talk. I was wondering if you're using the ARM. Here I am.
Sorry.
Sorry. Maybe I should lift it like this so that you see where it's like. Are you using the ARM block functional model written in System Verilog in order to verify your XI4 designs?
Not in a systematical way. I've done this, but I've re-implemented, let's say. Actually, that's the kind of thing that I've re-implemented in my library, so I don't really use ARMs.
Okay, many thanks.
Any other questions? Here in the back.
Hi, thanks for the presentation. One question about synthesis. Don't you end up with a lot of warnings?
Not at all.
What you have? Not at all?
No.
Okay.
What do you expect? What
No,
kind of warnings?
if you have vectors that are too long and then you don't use some of the bits, you would end up with warnings at synthesis, which is something we don't want to have usually.
Well, it depends on the tools, but of course the tools like to say when they strip a signal, so of course you get this kind of information, but it's expected. Most of the time I think it's a note rather than a warning, but...
Yeah, it could be a note or, yeah, it depends on the tool, but then you end up with a lot of messages that are not relevant to exactly what you're doing.
Yeah.
But you don't suffer from that.
Not so much. I
Okay.
mean, that's the expected output anyway, to have stripping of unneeded wires. So, yeah.
Okay, thanks.
Anybody else? Yes.
Hey, thanks for the talk. I was wondering if you...
A little closer to the mic, please.
Can you hear me now? Okay. So I was wondering if there's some mechanism to detect misconfiguration. So like if the master supports strobing and the slave does not on axis stream, can you detect it? Obviously, this shouldn't happen, right?
The whole point here is to have constant configuration record in like the top level design where we give out this exact constant to each and every block so they all share the same configuration just by design. You don't copy all the configuration parameters because you create a constant and just pass it along everywhere. So it avoids discrepancies like I have set the configuration to be this on this block and this on that block. It should not happen because you only have one constant.
Yes, but then you basically have to know what the slave does. So you have to know if the slave supports strobing or not. Is that correct?
I'm not sure I get your question, actually. Either your slave block can support strobing, and that's fine, or it cannot, and it may like have static assertions in the entity to just say, okay, I cannot handle this.
Okay.
This is the kind of thing you can do, actually.
Oh, like asserts.
Yeah.
Okay.
Like say, oh, I cannot support your configuration. That's permitted in the end. But having generic infrastructure and having generic blocks are two different things. Generic infrastructure is needed because you cannot predict how it will be used. But let's say you have a block that is not even talking about strobing, but just saying it only handles 32 bits of data.
Right, yeah.
We say, okay, I only support 4 byte widths for the data path, and that's all. You can assert it early enough that the actual elaboration will fail if it's not respected.
Okay, thanks.
Maybe, yes.
Thank you for this presentation. I was wondering, I heard you said at the beginning of your presentation that you had to define signals for the biggest data width.
Yeah.
Is it because you don't use unconstrained data types?
Because of 93 compatibility, yeah.
Yeah, okay. And another question is, what kind of verification did you apply in the different blocks you were presenting? Is it functionally verified with coverage, for instance, or maybe formally verified? Or?
No, it's not formally verified. It's a a big bunch of test benches.
Okay, great. Are you using some kind of a systematic, how can I say, framework for verification?
You mean like
Or just,
VUnit or something like this?
for instance, yes?
No.
Okay. But it's
Mostly because they are providing BFMs that I already have inside, so I don't require to have external BFMs.
Okay, great, thank you.
Let's take a last question. Yes. You're already covered, you say? Interesting. Okay. Maybe then I can ask a question. So, is there much overlap with OSVVM with what you're doing here? Are you repeating something?
Sorry, I didn't get you.
What I'm saying is there some overlap with libraries provided by OSVVM?
Yeah, for the test bench part, basically, yeah. There is an overlap, yeah.
Yeah. All right, let's thank the speaker once again. Thank you, Nicolas.